Let's now examine parallel circuits installed on protoboards. Consider a parallel or side-by-side combination of three resistors, R1 having a value of 270 ohms, R2 having a value of 390 ohms, and R3 having a value of 560 ohms. Ideally, this parallel combination of three resistors should have a total resistance of roughly 124.2 ohms. Here's an effective but rather sloppy way of correctly installing this parallel combination of three resistors on the protoboard. One terminal of R1 is inserted into the collection of points constituting the node 20A through E, and the other terminal of R1 is inserted into the collection of points constituting the node 25A through E. One terminal of R2 is also inserted into 20A through E, and the other terminal of R2 is also inserted into 25A through E. Finally, one terminal of R3 is also inserted into 20A through E, and the other terminal of R3 is also inserted into 25A through E. There exist three separate parallel paths from node 20A through E to 25A through E. The ohmmeter demonstrates the resistance is close to the theoretical calculation for this parallel combination of three resistors. The circuit is effective, but it's admittedly a little cramped. Perhaps we could spread this circuit out a bit. Here's an equally effective but much neater and more accessible way of correctly installing this parallel combination of three resistors on the protoboard. One terminal of R1 is inserted into the collection of points constituting the node 20A through E, and the other terminal of R1 is inserted into the collection of points constituting the node 25A through E. An accessory wire joins node 20A through E with node 20F through J across the ditch. An additional accessory wire joins node 25A through E with node 25F through J across the ditch. One terminal of R2 is inserted into the node 20F through J, and the other terminal of R2 is inserted into the node 25F through J. An accessory wire joins 20F through J with the node 20A through E in the middle section over the bus strips. An additional accessory wire joins node 25F through J with node 25A through E in the middle section over the bus strips. Finally, one terminal of R3 is inserted into the node 20A through E in the middle section, and the other terminal of R3 is inserted into the node 25A through E in the middle section. The ohmmeter demonstrates the resistance is close to the theoretical calculation for this parallel combination of three resistors. Notice how much neater and more accessible this circuit is than our previous cramped configuration. Consider the consequences of inadvertent opens inside parallel circuits. Let's say one of the accessory wires linking the top of R3 is vertically offset by one row. The accessory wire is landed at node 19A through E in the middle section. However, the top terminal of R3 is landed at node 20A through E. Recall that rows are not connected. This is an open circuit. The ohmmeter demonstrates the resistance of this parallel circuit, including an open R3, is roughly 159 ohms, meaning that only R1 and R2 are actually in the parallel circuit, and R3 has been effectively removed from consideration. Be on the lookout for such mistakes. Although the wire from R2 and the top of R3 may be separated by fractions of a millimeter, they may as well be a mile apart because no conductive path exists between rows. Here's another effective and organized way of correctly installing a parallel configuration of three resistors on a protoboard. One terminal of R1 is inserted into the collection of points constituting the node 30A through E, and the other terminal of R1 is inserted into the collection of points constituting the node 30F through J across the ditch. An accessory wire joins node 30A through E with node 35A through E below. An additional accessory wire joins node 30F through J with node 35F through J below. One terminal of R2 is inserted into node 35A through E, and the other terminal of R2 is inserted into node 35F through J across the ditch. An accessory wire joins node 35A through E with node 40A through E below. An additional accessory wire joins node 35F through J with node 40F through J below. Finally, one terminal of R3 is inserted into node 40A through E, and the other terminal of R3 is inserted into the node 40F through J across the ditch. The ohmmeter demonstrates the resistance is close to the theoretical calculation for this parallel combination of three resistors. Consider the consequences of inadvertent shorts inside parallel circuits. Let's say R3 both starts and ends at the collection of points constituting the node 40F through J. Recall that all points within node 40F through J are connected. This is a short circuit. The ohmmeter demonstrates the entire parallel combination has been effectively shorted out due to the inclusion of the shorted resistor R3. If I was to strip away the insulating block, this would be equivalent to tying both terminals of R3 together with a 0 ohm short. Again, components go from node to node, and two terminals of the same component are never inserted into the same node. Do not do this. Moving on. Let's now take a look at how potentiometers interface with protoboards. You recall a potentiometer is a 3-terminal variable resistor. When inserted into a protoboard, each of the three terminals must be inserted into its own independent node. Consider this 500 ohm potentiometer, arranged such that one terminal is inserted to node 33A through E, the adjustable B terminal is inserted to node 34A through E immediately below it, and the remaining terminal is inserted to node 35A through E immediately below it. An ohmmeter from node 33A through E to node 35A through E demonstrates the potentiometer presents a fixed resistance slightly higher than 500 ohms regardless of the position of the adjustable screw. An ohmmeter from node 34A through E to node 35A through E demonstrates the potentiometer presents a resistance of roughly 420 ohms. With the ohmmeter in the present configuration, a spin in the adjustment screw changes this resistance to roughly 300 ohms. If we reposition the ohmmeter to check resistance from node 34A through E to node 33A through E, it demonstrates the potentiometer presents the remaining 200 plus ohms of resistance. Again, components go from node to node. This is the only correct way to install a potentiometer on a protoboard such that all three terminals are isolated from one another. Compare and contrast this correct implementation with this startlingly incorrect implementation where all three terminals are inserted into three of the 5 holes defining the single node 35A through E. All three terminals of the potentiometer have been effectively shorted out by the conductive clip forming this single row. If I was to strip away the insulating block, this would be equivalent to tying all three terminals of the potentiometer together with a 0 ohm short. This cannot and will not work. Do not do this. Components go from node to node. Let's now take a look at how special purpose electronic components interface with protoboards. Over the course of your enrollment in progressively more advanced electronics courses, you may have the opportunity to work with semiconductor or logic devices in the form of dual inline packaged or DIP components. These chips have 2 rows, hence the name dual, in a line, hence the name inline, on either side of their body, like a little bug. These components are meant to straddle the ditch such that one side of the chip is affixed to the nodes A through E, and the other side is affixed to the nodes F through J. Each pin is effectively isolated from every other. This is the only correct way to install a DIP format component on a protoboard. Compare and contrast this correct implementation with this incorrect implementation, where terminals on opposite sides of the chip are inserted into the same row. Every pair of terminals has effectively been shorted out by the conductive clip forming each row. If I was to strip away the insulating block, this would be equivalent to tying terminals on either side of the chip together with a 0 ohm short. This cannot and will not work. Do not do this. Components go from node to node. Here's another example of a dual inline package of switches consisting of 8 individual single-pole, single-throw switches. Each switch has 2 terminals and is electrically isolated from every other switch in this package. One can open or close each switch individually such that it makes or breaks connection between its individual terminals. The only correct way to install this collection of switches is so it straddles the ditch such that one terminal of each switch is on one side of the ditch and the other terminal of the switch is on the other. The only way to get across the ditch is through a closed switch. The ohmmeter demonstrates there is no connection from node 45A through E to node 45F through J. This switch is open. When I close the switch in that particular row, the ohmmeter demonstrates there is now connection from 45A through E to 45F through J. This switch is closed. Compare and contrast this correct implementation with this incorrect implementation, where both terminals of each switch are inserted into the same node. Every switch has been effectively shorted out by the conductive clip forming each row. If I was to strip away the insulating block, this would be equivalent to tying both terminals of the switch together with a 0 ohm short. It's glaringly obvious that a 0 ohm short bridges the switch, and the switch's ability of making and breaking electrical connection is negated. This cannot and will not work. Do not do this. Components go from node to node. Alright, we're just about finished. Before we go, a final note about protoboards is this. Be a gentleman and don't just ram it in there. Some electrical components are exceedingly fragile and necessitate a little dexterity and aim prior to seating them in place, especially potentiometers and dual inline package components. It is super easy to bend or break a lead such that no connection exists. Outwardly, things may appear to be connected, but reality may be startlingly different. You note some of the troubleshooting scenarios I presented in this lecture result from the subtle misplacement of a component or wire on the order of one row. Pay attention to detail and make sure components intended to be connected actually are connected by making sure you land them on the same node. If you miss a connection by even a millimeter, you may as well have missed it by a mile. Close inspection from several angles should reveal the fault. Pay attention to detail. Check your lab partner's work and have your lab partner check your work. Finally, if you're given the option, it's a recommended practice to construct circuits on your board exactly like the way they look on the schematic you're given. If resistor R1 is to the left of resistor R2, by all means, put resistor R1 to the left of resistor R2 on the board. While not electrically necessary in all scenarios, having a one-to-one correspondence between the schematic representation and physical reality sure makes taking observations and troubleshooting much easier. Finally, I would like to dispel the common misconception among students that the board is ever at fault. Now, I am not ruling out the remote possibility of a bad board, but it is not the board. It has never been the board. It never will be the board. It is your circuit on the board. It is the manner in which you constructed your circuit or the manner in which you are attempting to make observations about your circuit. It is you, and you need to figure out how to use the board to construct your circuit properly. Figure it out. That's your job. I never said it was going to be easy. Pay attention to detail and use the skills you've developed. If you've been following these lectures in their intended sequence, you know how to use an ohmmeter and should understand the influence of shorts and opens. Put these skills to use and do not tell me your board is broken. Your lab partner? Yeah, they're broken. You touched them last. Either fix them or throw them away. Your choice. All right, that about wraps it up for this brief introduction to the Protoboard. In conclusion, this lecture took a close look at a circuit building environment commonly utilized in lab and research and development settings known as a prototyping board. We use the ohmmeter function of the DMM to determine how the board is constructed, build a couple demonstration circuits on a prototyping board, and discuss common misconceptions and pitfalls about prototyping boards and the steps you need to take to discover and avoid them. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.